Welcome everyone, and thank you for joining us today for DigitalGlobe's lead webinar series, Learn, Engage, Act, and Discover. My name is Becky Schneider, and I'm the Marketing Programs Manager at DigitalGlobe, and I'm also going to be your host for today's webinar. But before we get started, I want to pass along a few tips to everyone to keep in mind while viewing today's webinar presentation. First, all attendees are on mute. So to ask a question, you can use the Q&A chat box feature that's located at the right-hand side of your screen. All questions will be answered at the end of today's presentation. Attendees have the option to view today's webinar in full screen. To view in the full screen mode, you can click the full screen X that's located at the very top of your screen. And lastly, a link to today's webinar recording will be sent to everyone via email within the next 48 hours. Today's webinar is titled Exploration, Mining, and Environmental Applications of Worldview 3, and it will be presented by Exploration Mapping Group, a DigitalGlobe Information Partner that specializes in providing remote sensing and information management services for global natural resource companies. Global explorers rarely have opportunities to benefit from step changes in exploration technology, but the newly released Worldview 3 satellite data represents the most significant advance in geological remote sensing since the launch of ASTER in 1999. Using a variety of mineral exploration examples, Exploration Mapping Group will show Worldview 3 applications for precious metals and rare earth element exploration, mining, and related environmental applications. Today's webinar will be presented by Dan Taranik. Dan is a Managing Director at Exploration Mapping Group and has over 20 years of mineral exploration and mining experience. Prior to joining Exploration Mapping Group in 2012, Dan worked internationally for Rio Tinto, Anglo American, and BHP Billipen with significant project work completed in more than 30 countries. Dan was on the committee of the Geological Remote Sensing Group in London and was its chairman for 4 years. So without further ado, I would like to welcome Dan, and let's begin today's webinar.
Welcome everyone, and thank you for attending this webinar on exploration, mining, and environmental applications of Worldview 3. My name is Dan Taranik, and I'm the Managing Director of Exploration Mapping Group based in Las Vegas, Nevada. By way of background, Exploration Mapping Group has a global focus on exploration, mining, petroleum, and environmental remote sensing. We are specialized in satellite imagery, large area mosaics, alteration mapping, and related geoscientific data integration and interpretation. We are very pleased to be DigitalGlobe's first digital dedicated geoscientific information partner. As an information partner, we provide you with industry-specific expertise, the highest quality geometric and atmospheric data. We have satellite tasking priority second only to the military. We have lower cloud cover minimums, and we have very favorable pricing. For those of you who may not be familiar, this is a timeline showing the development of high-resolution satellite technology. DigitalGlobe as a company has figured prominently and has a long and distinguished history of high-resolution satellite imagery, beginning with Early Bird in 1997 at 3-meter resolution, Iconos in 1999, which was the first commercial satellite with sub-meter pixel resolution, then QuickBird in 2001, GeoEye in 2008, and leading into the series of Worldview 1, 2, and currently the Worldview 3 satellite launched in 2014, which we'll discuss in more detail today. If you haven't used Worldview 3 data yet, you're in for a very pleasant surprise. It has the highest technical standards commercially available in a number of very significant categories. First and foremost, it has the highest spatial resolution commercially available, with a 31 centimeter panchromatic band, 1.24 meter visible and near infrared or VINER bands, a 7.5 meter shortwave infrared bands, or SWIR bands. And it also has a swath width of 13 kilometers. The second important factor about WorldView 3 is that it has the highest satellite spectral resolution commercially available, with a total of 17 bands. No other satellite can match WorldView 3 with the 8 bands of Wiener and 8 bands of SWIR plus the panchromatic band. Another really important feature that we'll discuss in a moment is the signal-to-noise characteristics are outstanding, and we'll look at some relative numbers in just a minute. Another feature I'd like to point out is that WorldView 3 has positional accuracy of 3.5 meter CE90. CE90 stands for circular error at 90% confidence. And in many cases, it's even better than that without ground control. So WorldView 3 has no rivals for its enhanced positional accuracy. The next point I would make is about atmospheric corrections. These are done internally at DigitalGlobe and exploration mapping with what are called CAVIS bands. That is an acronym for cloud, aerosol, vapor, ice, and snow. And these are used for detailed atmospheric measurements and correcting your data to very accurate ground reflectance. Another really important point about data quality is the collection capacity of WorldView 3. It can collect up to almost 700,000 square kilometers of high-resolution data per day. And in any one go, it can collect up to 3,000 square kilometers of full-resolution data per pass. So we are ready for very large projects. Another final point I would mention is the possibility of daily revisits. WorldView 3 is able to collect any location on Earth daily with a 1 meter or better resolution, and every 4.5 days it can collect the full complement of 17 spectral bands. You can see a comparison of WorldView 3 with the spectral coverage of ASTER and Landsat on the right-hand side of the slide for comparative purposes. So just a quick demonstration. One of the first things you'll notice is the sharp, crisp detail of the higher resolution bands of WorldView 3. This slide shows the 3 spatial subsystems of WorldView 3 along the bottom. The 30 centimeter highest resolution in the lower right, 1.2 meter in the middle, and 7.5 meter on the lower left along the bottom. Compared to the spatial resolutions of ASTER and Landsat pixel sizes along the top, the 15 meter, the 30 meter, and 90 meter pixels. So it's quite a striking improvement, and you'll be amazed at the detail you can see with it. Another feature that you'll really appreciate are the atmospheric corrections mentioned earlier, done with the CAVIS bands. It's really amazing. Every data set that I've worked with has had incredibly sharp detail, even if there's persistent smoke or haze or thin cloud cover is present. Another thing that you will notice, a very noticeable benefit, is shown in this slide with WorldView 3 signal-to-noise compared to ASTER, for example. The signal-to-noise is ranging from 620 to 860 across the Wiener and SWIR, and that's roughly a factor of 3 or 4 greater than ASTER, just for example. So let's start looking at some examples of WorldView 3 data for exploration and mining. I wanted to note up front that we aren't using any examples of our clients' data. All the examples in this presentation are recent archived WorldView 3 samples processed specifically for this presentation to show some of the capabilities of the instrument. This first example is the Bullfrog Mining District, just north of Las Vegas, Nevada, and east of Rhyolite, California. And it's a known, historic, and recently revived gold mining district. It has volcanic-hosted high-grade lode gold deposits with tabular vein and shear zones, as well as disseminated gold. The regional structures are normal faults trending north to northwest with dips often exceeding 20 degrees. From 1989 through 1999, the mine produced over 2 million ounces of gold and 3 million ounces of silver. And the mine owner, Barrick, won the Nevada Excellence in Mine Reclamation Award twice for its post-mining land use. Corvus Gold is a junior exploration and development company led by an experienced management team and has recently found a new resource estimated over 2 million additional ounces. I've included on the right of this slide some data showing the very high level of 30 centimeter detail merged with the natural color image. You can clearly see individual cars, lamp posts in their shadow. You can even see oil stains where cars would normally park. So there are stripes, road separator stripes in the road that are visible, and small little boulders that form the edges along the parking lot. So it's really incredible detail. You can see down to the level of individual outcrops in the field and even specific bushes and tumbleweeds in this part of the world. This slide is a fairly typical example of what Exploration Mapping Group produces for its clients. This figure shows alteration mapping of two iron minerals, hematite and goethite, using WV3 Wiener bands only, this being one of perhaps 8 to 12 to 15 different alteration layers included as a deliverable for our clients. You can notice here the mapping of hematite in red and goethite in green. They're both favorable indicators of alteration in metal-bearing systems, and they're something that exploration geologists are normally interested in and look for with remote sensing data. Note also the spectral curves on the right for hematite and goethite from the USGS Spectral Library, which, along with ENVI software, are invaluable tools for processing WorldView3 data. The alteration mapping techniques we use vary widely, however. Sometimes indices work, spectral matching and mixing approaches are common. Spectral shapes are relatively new, but we're finding those to be quite useful. And there are various other multivariate techniques depending on the commodity of interest and the surface expression of the metal or ore that you're interested in and the local terrain. In the second image, we superimposed a kaolinite alteration mapping class, and this is appropriate for gold deposits and hydrothermal alteration. So this is really a very good start, an excellent product for exploration teams to highlight the iron minerals, hematite, goethite, and the clay alteration and head in the field. In our next example, Cuprite, Nevada is one of the most iconic remote sensing sites in the world. That's because of its complex geological composition and the clear desert conditions of Nevada. It's been used as a calibration site for almost every field spectrometer, airborne scanner, and resource satellite ever flown. AIS, the GER scanner, Geoscan, HIMAP, SPECTIR, SPECTRUM, CBAS, AVERIS, Landsat, ASTER. This area is not famous as a mining site, but as a test site. And also the discovery using remote sensing of the mineral buddingtonite, the rare ammonium feldspar, by Alex Getz and his team at NASA's Jet Propulsion Laboratory. That team also coined the term hyperspectral from the work that was being done at Cuprite. Cuprite continues to be a subject of much study and research, as most recently shown by the Society of Economic Geology publication by Swayze and several others in 2014 from the U.S. Geological Survey. So let's look at some imagery. We have some typical color composites produced to show a separation of the rock types and alteration of the area. Here again, like the Bullfrog Hills, the alteration mapping is shown in somewhat more detail at Cuprite, with yellow, green, and brown colors representing high concentrations of silica and clay alteration minerals. These are the end members we were able to map at Cuprite with WorldView3 data and showing the various gradations of alteration intensity. We use the USGS Spectral Library for unmixing, and I have, in addition to these classes, have seen the signatures and spectral bases for mapping buddingtonite the cuprite using WV3 data, but I'm not entirely convinced it can be mapped consistently without prior knowledge that it's there. So I put a question mark after it. Two things really stood out when working with the cuprite WV3 SWIR data for the first time. The first was the ability to map the opaline chalcedony center of the main cuprite alteration system without having access to the thermal infrared bands. Normally, quartz-rich rocks are best mapped in the thermal infrared, but there is a spectral basis for mapping it with WV3 if you look carefully at the spectral data in the WV3 band passes. The second point that came across very strongly with the cuprite data is the extremely high signal-to-noise shown in the SWIR data. This SWIR data only, there's no Wiener, but if you look at Stonewall Playa to the southeast of the main cuprite alteration center, we're mapping a mineral class called muscovite, smectite, montmorillonite specifically, also showing a separate, distinct opal chalcedony occurrences that can be identified across the playa. This is incredible resolution, and normally playas, such bright targets as that, might be masked, but with the signal-to-noise that we have, it is very well expressed at cuprite. And I've only seen this with hyperspectral data before, so it's a real testament to the high signal-to-noise ratio of WV3. Our next example is the Mountain Pass rare earth element deposit in California. This is a 1.4 billion-year-old Precambrian carbonatite intruded into gneiss, and it has very high grades of 8 to 12% rare earth oxides, mostly contained in the mineral bastnasite, and it's regarded as a world-class rare earth mineral deposit. The metals produced from this mine include a number of rare earth metals: cerium, lanthanum, neodymium, europium, four metals that will only get increasingly more important in the years ahead because of hybrid cars, which take 10 pounds of lanthanum on average. And it's also the metal part of the nickel metal hydride batteries. Europium is used in color display devices and fluorescent bulbs, the new energy-efficient incandescent bulbs. And neodymium magnets have made heavy, chunky tech much lighter and cheaper, and it's in all your smartphones. So it's a very interesting deposit. Mountain Pass, like cuprite, has been the subject of many airborne and satellite remote sensing studies for a number of years. Significantly, and quite recently, 2 remote sensing-oriented PhD theses were completed in and around the deposit. Marilyn McDowell and Fred Cruz published McDowell's PhD thesis in 2014 and used the Mountain Pass area as a test site for integrating Wiener SWIR AVRIS with 15-meter resolution and master data, airborne thermal 35-meter pixel data, and we're able to find several distinct rare earth element-bearing spectral end members, even with those relatively coarse pixel sizes. David Turner finished his thesis just a year ago in April 2015 with Ben Rivard at the University of Alberta, and his thesis was focused on rare earth element spectroscopy and concluded that hyperspectral imaging can detect rare earth elements in drill core to be used directly to estimate ore grades. I would just mention I have my own personal experience at Mountain Pass many moons ago, and I'm dating myself now. I was the first full-time employee for analytical spectral devices in Boulder, and I used the first ASTER spectrometer to measure samples in situ at Mountain Pass. And we had fantastic success even then with the instrumentation of the day. And there were dramatic absorption features, primarily bastnasite and the Wiener. So here's an example of how we built up the color composites. This is what we started with. The atmospheric corrected product is called ACOM. We then applied a linear stretch just to get some more color in the image. And finally, we have a natural color saturated image of the mine area that shows iron minerals and other cover types in some detail. So we have about maybe 6 or 8 different color composites that we might use in a given area to show different things: iron minerals, clay minerals, vegetation cover, etc. So we tried various unmixing approaches with the USGS spectral library for rare earth elements, which consists of neodymium and monazite. But we did not have any luck. We had a lot of false positives. But asking around with my colleagues, we received actual bastnasite spectra, the major ore mineral at Mountain Pass, from both David Turner and Ben Rivard at the University of Alberta and Rob Green at JPL. And it was sure work to get a spectral match and identify the areas of high bastnasite abundance that you see here. I've met the chief geologist for the mine, and we're going to field check this now that the results have been finished. So if you're interested, please follow up with me. Final example I wanted to show today is some work in progress. Not climate data, obviously, it's Beatty again, but it's an illustrative example using Beatty as a test site for demonstration purposes. You can see the city of town of Beatty on the inset to the right. Beatty is a hyper-arid desert region, but we're still able to map a number of vegetation parameters based on absorption features such as pigments, plant structure, water, cellulose, lignin. And in this case, we were able to show that we can actually measure vegetation stress. And we're currently doing a project like this for a mining client, but we thought Beatty was a good example to show the same sort of analysis. And so you can measure various parameters, and we were able to find really good indicators of vegetation stress and be able to monitor that as a baseline going forward at any given time interval. We've compiled a number of vegetation-related parameters that can be measured with bands available in WorldView 3. There are new bands in WorldView 3 for coastal blue, red edge, yellow, near IR1, near IR2, and these were specifically designed to allow new capabilities of mapping vegetation and vegetation health parameters. Using a number of the classic indices, things like leaf area index, NDVI, etc., and then combining those with the new processing techniques that are possible with the additional bands allowed us to map 4 spectrally distinct vegetation species in Beatty. The name of the main community event center in Beatty is Cottonwood Park, so we're reasonably certain that we know at least one vegetation type present in the area. So we're about finished, and I would just like to make a few closing comments. If you haven't tried using WorldView 3 yet, there are sample data sets on the DigitalGlobe website for cuprite in the Ukraine, I believe, and you can see the link here in the PowerPoint deck. If you decide you have an area of interest that we can look at the different probabilities of successfully collecting data in your region and the feasibility based on WorldView 3 satellite demand, and come up with probability, feasibility of how soon your data can be collected. So that's quite a useful feedback that lets you know how easily and how soon we can collect your area. So in closing, I would recommend that you define areas of interest for WorldView 3 And exploration mapping can search the WorldView 3 archive for existing data. We can detail the deliverables for the commodity style that you're interested in, the terrain that you're working in. We can provide the cloud cover and new collection feasibility results we just saw and let you know about delivery time frame and costs. So that's the end of the presentation, and I want to thank you for your time. And if there are any questions, please let me know.
So thank you, Dan, for your very informative presentation. At this time, we're now going to open up the Q&A portion for today's presentation. If you do have a question for Dan, you can type that question into the Q&A chat box. So Dan, thanks again for your presentation. I had a couple of questions that came in while you were presenting. And one of those questions is that a listener wanted to know, what are the advantages of WorldView 3 data versus Landsat, ASTER, or airborne hyperspectral?
Right. Thank you very much, Becky. I think something that really jumps out is the signal to noise characteristics of WorldView 3, particularly in Arctic terrains. We've never had really good illumination of northern targets, Finland, Sweden, Greenland, Canada, of course. But with these signal to noise characteristics and the typical low sun angles, we're really going to see a change in improved signal for those areas. So, you'll see advantages with WorldView 3. Regarding Landsat and ASTER, those two instruments, both data sets cover much larger areas. Landsat 180 by 100 kilometers, 180 by 180, and ASTER 60 by 60 kilometers. ASTER has TIR bands, which is great, but they're 90 meters, so you can't really get to outcrop scales. It's more of a gross lithological mapper. ASTER has band 9. The channel near 2400 nanometers, which is not on WorldView 3, but you really don't need that specific band. It only acts as a shoulder for carbonate, chloride, epitope absorption features that can be mapped with ASTER band 8 and WorldView SWIR 8. However, WorldView 3's Wiener bands, especially at 1.2 meters, can help resolve the iron-related absorptions of chloride to help differentiate it from calcite and dolomite. So really, in summary, it's the high spatial resolution and high signal-to-noise ratio of WorldView 3 that set it apart. So in mature districts, you should be able to see alteration systems that have perhaps been missed. Oh, and there's one other really interesting thing that we're seeing. Most of our current client projects are overseas, and we're doing a lot of work in jungle terrains, heavy canopy areas like Brazil, I think Southeast Asia, Africa, and we're seeing road tracks, cattle paths, even human walking pathways that show alteration that you would never pick up with ASTER or Landsat. So this really high resolution data kind of opens up the applications of Wiener SWIR remote sensing in heavily vegetated terrains, which is quite remarkable.
So moving on, we've got several more questions for you that came in. One of those questions is kind of what is the cost of the data or project per square kilometer, and do you offer any type of discounts for education or academics?
I'll probably take the costs offline. They are fixed. They don't vary from client to client, but there are resellers, there are other IPP people on that sell data. So I'd rather have clients who are really interested in that contact me at my email address or the company website, and I can inform about those numbers. But yeah, let's leave it at that.
Okay, for that listener, I will include Dan's email address in the chat box and definitely follow up with him offline to continue the conversation. Another question that came in is a listener wanted to know How do you define vegetation stress with 3.5-meter resolution?
Well, you could identify vegetation stress with, even with 90-meter data or with 1 centimeter data. Pixel size doesn't really affect your ability to map, but traditionally people have looked at NDVI or the similar water DVI and countless permutations of red, green, blue, and near infrared to look at vegetation health parameters. But with WV3 data, as I mentioned during the body of the talk, you have a yellowness band, you have a very specific and narrow red edge band, and the 2 near-infrared bands have been split and placed exactly to measure environmental vegetation characteristics. So there's a whole new range and quite a bit in the scientific literature on historic hyperspectral uses of those specific bands. So it's really opening a door to a large number of new processing techniques, much more advanced than NDVI approaches.
Another question that came in as a listener wanted to know, is there a special type of software that you're using for image processing?
Yeah, we have a number of different packages, and some of our employees are more specialized in one software or other, but my own personal preference is Envy. A shout out to Harris and Excelis and all the good people there. It is the only software package commercially available that does unmixing and manages spectral libraries very well. I'd also give a recommendation, a shout out to Ray Kokele at the USGS in Denver, who has an add-on to Envy called the Spectral Library and related software. And really, there are so many bands. We're talking about 17 bands of WV3 data that simple approaches don't apply anymore. You really need to be able to unmix and use software that unmixes. And Envy is the only one I'm aware of that does that well.
Another question from a listener is they'd like to know, how do you deal with the oxidation of minerals once they are exposed to UV and water that changes their spectral signature?
Yeah, that's a great question. Clouds, playas in desert environments, snow, ice, shallow water, coastal areas, all of those are false positives and have the effect of acting like a prism and making rainbow signatures, leading to false anomalies in almost any kind of satellite data. So some approaches have been to physically mask those out with polygons and remove them, leaving a cookie cutter of an image without any of those artifact areas. But again, now that we have so many bands, we're finding that you can do a lot of spectral math to minimize those areas just within your processing. So you can calculate burn indices that would normally be a confuser for the shortwave infrared clays. We have a big project now in an area that has a lot of ice and snow, and we're doing that spectrally rather than spatially. So tools in Envy or any other software can allow you to remove those artifacts as best you can.
Another listener wanted to know, have you looked in object-based image analysis techniques for such projects?
I'm not quite sure what, I've heard of object-oriented, but I'm not quite sure what that means in a remote sensing sense. Maybe if the user could elaborate, I could have another attempt. I'm not quite sure how to answer that.
Okay, he's typing some more information into the chat box, so we'll, let's see, so we'll move on. Another listener wanted to know, is, in the future, are there any other bands not included on WorldView 3, but maybe in the future that you'd like to be commercially available?
Well, that's an excellent question, too. If I had a wish list, it would definitely include high-resolution thermal. I would love to have 8 bands in the TIR, but the reason ASTER has 90-meter pixels from satellite altitudes is that it's very hard to get good signal-to-noise. But with Moore's law and changes in technology and detection technology, it's not unlikely in our lifetimes we're going to see something with hyperspectral thermal. The other area that has quite a lot of research potential, which I really haven't seen expressed, is the ultraviolet. I have done some work in a petroleum company many years ago, and we were looking at the signature of ultraviolet rocks. And anyone who's gone to a geological library will visit the darkened room and see the oranges, lime greens, and blues in the UV. And that same sort of thing has a lot of potential, but huge, thick atmospheric masking in the UV region. So that's a challenging target. I think finally, final idea is the 3 to 5 micrometer thermal range, not the normal 8 to 12 micrometer that ASTER measures, but the 3 to 5 has quite a lot of geological utility too, and you see it in the scientific literature, but not a lot of instruments, even airborne, are mapping that region, but I think that has great geologic potential as well.
Another question that came in is a listener wanted to know how can higher spectral resolution improve mineral exploration on dense vegetative areas?
Well, remember, remote sensing is largely, almost always, a skin effect. So in the Wiener and Swer, you're only getting penetration of the top few micrometers of vegetation. So if you're in triple canopy jungle in Brazil, you're not going to see below those top canopy leaves. I mean, that's just a law of physics that we can't get around. But what you do have are holes in the trees that look down at road paths, as I mentioned earlier, stream banks. With this high resolution, you can actually see alluvial material next to running water that you wouldn't have seen with the averaging of ASTER size or Landsat size pixels. So there's no magic bullet. We're not going to penetrate vegetation, but it's just the higher spatial resolution that unlocks this new potential.
So going back to the previous question that came in, a listener, that we needed some more information, that was on the object-based image analysis, and the listener came back with what he's wanting to do. What he's wanting to know is, have you done classification based on image objects rather than single pixels?
Oh, I see. Okay, yeah, classification. Yeah, we definitely have. If you, in fact, I've got a project right now where we acquired new WorldView 3 data. I might add that normally when we acquire new data with WorldView 3, our experience is that we've acquired it within 2 weeks of signing the purchase order. So, you know, so far so good. We're getting great response times, although that can vary where you're working in the world, etc. But that client went into the field and did a very large field spectrometer survey, and we're now working through hundreds of field spectra at a number of sites across the newly collected scenes to calibrate the mineral response. And, you know, this is really helpful. So I hope this is answering your question. Yes, you can do classification from field-based data and then try to find out, in a simple sense, where else in that image the same spectral signatures occur.
Your next question is, a listener would like to know, what format are the products delivered in?
The raw data cubes come to us as raw, and we apply with Cavis bands and other radiometric information the actual data format is called TIL, so it's a tiled format, even if they're singular contiguous bands. But for all of our clients, we deliver not only that very raw data, but also a clean, finished cube with the Wiener and Swirr aligned as perfectly as we can get it, and the atmospheric corrections applied. So in addition to the products we deliver, you would have a clean, finished cube to do any specialized processing if you have in-house software or you have other things in the future that you'd like to map that didn't occur the first project. Did that answer it?
I think so. Also, is that information, is that something that you can send like via FTP, or is that something that you send offline via another type of media, whether it's a hard drive or DVD, et cetera?
Yeah, we always do both. The key images, the key deliverables in the project, we normally deliver via FTP, and individual images can be anywhere from 2 to 10 gigabytes, particularly the pan-sharp and color composites are quite dense. And then the alteration mapping projects with several layers, those are quite large images. So key images we ship by FTP, and then at the end of the project, when everything's done, we ship everything on an express mail courier magnetic hard drive. So you get both of those options.
So another question that came in, a listener wanted to know how different and better is the data quality when comparing ASTER to WV3 data?
Yeah, there was a slide that we showed on that, and the quality, you know, ASTER is a wonderful instrument, and we still use it. We still process it for clients even right now. But it was designed 20 years ago in the late 90s, and it launched in 1999. And there's a limited archive of data that was collected between 1999 and when the Swirr part of ASTER failed in 2007. So that archive's canned, and they're not making any more, or they are, but it doesn't collect the Swirr bands correctly. And you know, the signal to noise of WV3, the characteristics, it's between 600 and 900 in the Swirr and Wiener for ASTER based on DigitalGlobe signal to noise figures. And that's a factor of 3 or 4 times what ASTER signal to noise has. And if you add the spatial resolution, the smaller pixels, you know, it's really an extraordinary quality improvement. And as I mentioned before, in Arctic terrains particularly, which have historically had low sun angles and short summers, you know, we'll be able to see quite a lot more signal in those areas from a mineralogic, geologic perspective.
So we're going to take a couple more questions before we close out today's webinar. And Dan, another question that came in as a listener wanted to know, how long does it take to task the satellite for new acquisitions or projects?
Yeah, great question. You know, that varies around the world. There are basically 3 states of data that we charge for. One is archive data that already exists. It's in the archive. We can pull it and process almost immediately. Second condition in most of the world is a standard demand situation where new satellite tasking is required and the countries aren't too difficult. And it only takes about 2 weeks to acquire the data, depending on where you're at in the world. If you're in Papua New Guinea or the high Andes, cloud cover can be a challenge and take longer. But the third state is our high demand areas in the world, and that applies to Middle Eastern countries, Eastern China. We have a chart in this presentation in the webinar that shows the high demand countries, and you can send it to you know.
Oh, I think we lost you, Dan. Are you still there?
Yes, I'm here.
Okay, I thought I heard you fade out. Moving on, another question that came in, a listener wanted to know if you could briefly comment on how extractive layers such as limonite can be brought into a GIS application such as MapInfo?
Yeah, good stuff. I used to use MapInfo quite a lot. That was my favorite preferred GIS many years ago, but I've personally migrated over. This is no commercial recommendation. It's just my own preference, but I'm completely on ArcGIS now. And as you've mentioned, it's possible to vectorize the alteration polygons and mineral alteration occurrences and move those into the GIS so they can be overlain with geophysics or geochemistry, what have you. So this is a strength of Envy that allows you to polygonize the results, and it could be moved into MapInfo that way using the shapefile intermediate format. I hope that answers it.
Here's another question. The listener wanted to know, do you do any type of pollution identification work over tailing dams?
Yeah, definitely. That is the kind of project we're involved with now. I don't want to mention specific client work, but anyone who follows that space would know the mining disaster we're looking at. But I guess there are 2 or 3 points I would make about that. One is you're looking at the change of an area, the spatial change, like before and after, say, a dam breach. And then the second thing that we're trying to measure on a consistent time series is the vegetation health change, to see if we can look at those examples we showed of vegetation stress, yellowness, red edge, separation of near infrared 1 and 2. And the final point I would make around that is vegetation species identification. That we have one client who has an invasive species around their mining operations, and they wanted to map that, and that's what got us first interested in this whole area. They were saying, can you map this invasive species? And it turns out you can. That if you overlay enough of these environmental spectral indicators, you effectively get a fingerprint for the different species that exist, and that allows you to map them.
So we're going to do one more question before we close out today's webinar, and the listener would like to know, what other ore deposit types do you think WV3 will be useful for?
Yeah, that's a really good question. In addition to base metals like copper, the precious metals, gold, the rare earth element examples that we have seen in this presentation, we definitely are getting some good results on aluminum and bauxite exploration, and we can map that with certainty. There are iron ore indicators. We've got a lot of experience on mapping that, and iron ore is quite a good area. And I would just say anything in northern climates where the sun angle is normally low and has poor signal, anything in jungle terrains, we've got whole new capabilities now with the high resolution, high signal to noise.
And with some of these ore deposit types, does this also include like diamond exploration?
Yeah, definitely. I worked, many years for Anglo American, and we had projects with De Beers, and I'm familiar with the spectral characteristics of the kimberlites and what can be found with the resolution that we have. And yeah, absolutely. The shortwave infrared has got, some great potential for the diamond terrains. And yeah, that's definitely up there.
So that's going to close out the Q&A portion for today's webinar. I'd like to thank Dan again for his very informative presentation, and I'd like to thank all of you for attending today. If you have additional questions or if you would like additional follow-up, I encourage you to reach out to Dan directly. Dan's contact information and company website information is listed on the slide, as well as for those that are attending today's live webinar, I have included Dan's email address in the chat box. So that's going to conclude today's webinar. I thank everyone for attending, and we hope to see you at future webinar events.
Thanks, everybody.